Okay, I think this is recording. Hopefully it is. I already recorded it once and the microphone wasn't on. So let's do it again. Second time for me, first time maybe for you. Let's go into the parts of a chemical equation. So this is our first lecture. Sorry, my cat is literally knocking stuff off the kitchen table. This is our first introduction to chemical equations and balancing them. So the parts of the equation, okay, this is important. You have what are known as the reactants, and the reactants are the substance or substances, you can have more than one, usually we do, that participate in the chemical reaction, and they are going to be represented on the left side of the arrow. So the reaction arrow is just an arrow there in the equation. Everything on the left is considered a reactant. The products is a substance or substances that form in the chemical reaction. They are represented on the right side of the arrow. So this is my product. So in this case, I have hydrogen gas. I know it's a gas because there's a little G here. You don't have to worry about doing that. It's not something that we'll focus heavily on, but you can if you know the state of matter that your substance is, you can add it. So we have hydrogen gas plus oxygen gas yields liquid water, okay? That's the chemical equation. Now, the other parts of this are the subscripts, these little numbers, okay? These are subscripts. Those come from when we name and create the formulas, all right? Those are your oxidation numbers, or they come from your di, tri, tetras, however you want to name your covalent compounds. The big numbers, okay, the ones that are big and out in front of the whole compound, those are your coefficients. Those are the ones that we add to balance the chemical equations, okay? So for a balanced chemical equation, both the kind and the number of each atom must be conserved. This means equal counts of each element on each side, all right? So I'll talk a lot about how many hydrogens do we have on the left? How many hydrogens do we have on the right? That number needs to be the same, okay? So in this, let's go ahead and we'll say the subscripts, keeping with the theme up there, all right? I'm going to label the subscripts in red. So up here in this equation, the subscripts are the little numbers, right? The coefficients are going to be in green up here, or circle those. The reactants will underline in blue, and the products will underline in purple. Okay, so we'll start with reactants. The reactants over here are sodium and chlorine. Okay, those are the reactants. The product is sodium chloride. Okay, so that's my product. These are my reactants. All right. We're going to circle the subscripts in red. I only have one, just that guy. And we're going to circle the coefficients in green. Coefficient, coefficient, okay? So this is just identification of the parts of a chemical reaction. Very simple stuff. Now, the math of what these numbers mean, it's all going to be multiplication, okay? So the subscripts come from the formula. Either they're your oxidation numbers or from your covalent prefixes, and they tell you how many atoms are in that particular molecule. Like water is always 2 atoms of hydrogen for every 1 atom of oxygen. You can't change that and still have the molecule water, okay? Coefficients, those numbers out in front, those come from balancing the equation, and they tell us how many molecules we have. And that is how we balance the equations. It's a combination of the subscripts and the coefficients. And it is a multiplication process, okay? You multiply the subscripts by the coefficient to get the total number of atoms. So like over here, this 2 tells me I've got 2 sodiums. The subscript 2 tells me I've got 2 chlorines. And then over here, this 2 gets multiplied across for both of them. So I have 2 sodiums and 2 chlorines, and that's a balanced chemical equation, okay? The reason for this, the why, is the law of conservation of mass, okay? So it explains the why that we have to balance our chemical equations. This states that during a chemical reaction, the total mass of the products must be equal to the total mass of the reactants. In other words, mass cannot be created or destroyed during a chemical reaction. It is always conserved. This video, I will link it on the Google Classroom. For some reason, I can't embed and record on my iPad a video all at the same time. It's asking too much. But what happens is they have an Erlenmeyer flask with a stopper on it, and inside originally is there's a clear liquid in this and a clear liquid in the test tube, and it has a mass of 158.2 grams. They turn it upside down so the test tube liquid pours out and you get this vibrant yellow, and they put it back on the scale, and guess what? The mass is the same. I will do a different demo for you for the conservation of mass when we're back together on Monday. Okay, let's get into some balancing equations. Here we have hydrogen gas and chlorine gas combining to make hydrochloric acid. So H2 plus Cl2 makes HCl. If you want to visualize this in terms of like pictures, you could think of your hydrogen atoms bound together, that's your H2, your chlorine atoms bound together, those are your Hoberfinkels, right? They come in pairs as two larger ones. And to make HCl, you're going to need one of the greens and one of the pinks. And if you just look at this visually, you're automatically going to be seeing that, hey, there's two greens here and there's one on this side, and there's two pinks here and there's one on this side. This is an unbalanced equation. To balance it, we have to add the coefficients in front of the compounds, okay, in front of the molecules. We cannot change any little numbers. So to do this, that means you're going to have to make two hydrochloric acid molecules, and we represent that by putting a 2 out in front. And now we've got 2 hydrogens, 2 chlorines. Wow, that was a bad 2. 2 chlorines. This 2 goes for both, so 2 hydrogens, 2 chlorines. Bada bing, we're balanced. Balancing equations is actually really fun. It's something like a puzzle. It's fun when you get into it. All right, let's take a look at this one. Hydrogen gas and oxygen gas combine to make water. H2 plus O2 makes H2O. Okay, so there's your picture, and you make a water molecule. It's got 1 green and 2 smaller greens, and you're like, hey, hang on, that's not balanced. You are correct. To balance it, what are you going to have to do is visualize it like this, and then represent it by adding a coefficient here. So how many total hydrogens does that make on the left? 2 times 2, so 2 times 2 is 4 hydrogens. We've got 2 oxygens. Over here, those multiply to get 4 hydrogens and then 2 oxygens, and that's balanced. Okay. Now, as I mentioned, you cannot change the subscripts. No changing. Cannot do that. Here's why. H2 plus O2 makes H2O. That's water, right? And if you're like, well, why can't I just add a little 2 here to make it a balanced equation? Well, you no longer are making water. If you do that, you're making, that's hydrogen peroxide, okay? And that is not the delicious water that your body needs, okay? So you don't be drinking that. So you cannot add subscripts. You can only add the numbers before the elements. And I will usually, like in this worksheet I've given you to work on, I'll put a little blank in front of the formulas. Those are where you're going to need to add your numbers, okay? So grab the worksheet that Jim gave you, and I'm going to help you with 3 of the problems just to kind of get you into the flow of it and give you a few pointers. So first one's pretty simple. You have nitrogen gas plus hydrogen gas makes ammonia gas, okay? You can keep track of your atoms and amounts like this in a little chart, or you can just write it under the formula. I don't care. So I'll demonstrate both. So for this one, for over here on the reactant side, I have 2 nitrogens, and here I have 2 hydrogens, and this is the separation. On the right-hand side, I have 1 nitrogen and 3 hydrogens. So right away, anytime you see an element that has a 2-3 combo, you're going to have to make 6 of them, okay? Because that's the first number that 2 and 3 go into evenly. So to make 6, let's see, I'll use purple. To make 6 hydrogens on the left, 2 times 3 gives me 6, so I put a 3 here. And to make 6 hydrogens on the right, 3 times 2 equals 6, so I put a 2 here. And when I do that, the 2 that I put down here also affects my nitrogens. So my nitrogens went from a count of 1 to a count of 2. And now you look and you see, okay, I got 2 nitrogens on the left, 2 on the right. Happy. 6 hydrogens on the left, 6 hydrogens on the right. Happy. This equation is now balanced. Okay? Easy peasy. Let's go down to number 6. So number 6 is a different type of reaction. It's a decomposition. You've got one compound breaking apart into component parts. We'll get into the identification of molecules and equation types later. Right now, I just want you to focus on balancing. So here, I'm going to write my numbers underneath. Maybe you like this method better. So here I've got 1 potassium, 1 chlorine, 3 oxygen. Over here I have 1 potassium, 1 chlorine, and 2 oxygens. And again, you see that 2-3 combo, right? Oxygens 3 on the left and 2 on the right. So I'm going to start by making 6. And to make 6 over here, I need to put a 2 in the front. That changes everything beside it. So my potassiums go from 1 to 2, my chlorines go from 1 to 2, my oxygens go from 3 to 6. Over on the right-hand side, I need to make 6 oxygens, so I put a 3, and that makes 6 here. And then I have to look at my potassium and my chlorine. Here it's 2, here it's 1. Well, that's an easy fix. I'll put a 2 out in front, and that changes all of those, and suddenly that equation is balanced. Okay, so I don't care how you keep track of your counts, whatever works best for you. You can make a little chart, you can write underneath, whatever works, you just have to be able to keep track of your atoms. All right, now skip down to number 10. I chose number 10 because it's got a polyatomic. The thing I want you to realize is the polyatomic ion, oh, dang it, that 4 should be a subscript. Sorry, I missed one. So it's SO little 4, think like that. When you see a polyatomic and you notice it stays as its bundle, go ahead and add parentheses, and you can see this SO4 bundle stays together. It doesn't break apart into sulfurs and oxygens. It makes it easier to count if you count it as a whole bundle. If you count it individually, you can, that's fine. Here you have 1 sulfur, here you have 4 oxygens. Over here you have, because there's 3 bundles, 3 sulfurs and 12 oxygens. I like to count them as bundles. As long as they stay together on both the left and the right, it's the easiest thing. So let's go through and make our counts. So we have 1 aluminum, 3 bromines, 2 potassiums, 1 bundle of SO4, 1 potassium, 1 bromine, 2 aluminums, and 3 bundles of SO4. Okay? So you see bromine is a 3 and a 1. You see the SO4s is a 3 and a 1. Potassium's a 2 and a 1. And aluminum's a 2 and a 1. So it doesn't really matter where you start. Choose a spot. And sometimes you may have to go back and erase things. So I do recommend doing this in pencil. Okay. So I'm going to start with my SO4 bundles because those are some big compounds, and that'll change other things as well. So I need there to be 3 bundles of SO4 on this side. So I'm going to plunk down a 3 here. That changes my SO4s to 3. That also changes my potassium. 3 times 2 gives me 6 potassiums, okay? Over here on the right, well, I better fix my potassiums. So I need 6 of them. So I put a 6 there. That makes 6 potassiums and 6 bromines. Well, now I got to go over to the right and deal with my bromines. I need there to be 6. So I need, what times 3 gives you 6? And that's going to be 2. So that changes that to 6. And that changes my aluminums to 2. And then I go over here to the right. And, goodness gracious, we already have 2 aluminums. Look at this. Let's double check. I've got 2 aluminums, 2 aluminums. I have 6 bromines. I have 6 bromines. I have 6 potassiums, 6 potassiums. I have 3 bundles of SO4, and I have 3 bundles of SO4. Bada bing, bada boom, we're balanced. Okay? So I hope you have fun with the balancing the equations. It's, like I said, it's kind of a nice little puzzle. If you get stuck on one, skip it and move on to another one, because sometimes you'll just be able to, you just get in a sticky spot and your brain doesn't see the solution. Don't just stop, but just skip that one and move on. You'll probably find others that you can do without too much trouble. And we will regroup on Monday and go over these and introduce the different types of reactions. So have a fabulous weekend.